Hey, hello everyone. Thanks for joining us. My name is James, and I'll be joined here by Parwant and Pierre, and today we'll be discussing the digital evolution of geotechnical monitoring. So we're from Terra Insights, which is the group of these brands that you might recognize. So RST from sensors and data logging, Measuran, lateral deformation or vertical with their shape arrays, 3D geomatics, Instar technology, and Syscom from vibration monitoring and strong motion. So some logistics before we get started. Feel free to ask your questions anytime. You should have a little window there that lets you put them in. At the end, we'll go through as many as we can. There's a lot of you here, so apologies if we don't quite get to yours. But after the webinar, we'll be sending out a bunch of subsequent material, an email with any resources that we've referenced during the presentation. So yes, the slides and so forth. But yeah, we're live, so feel free to ask those questions, and we'll have a nice discussion at the end. So before the webinar, we asked a bunch of you, what is smart geotechnical monitoring to you? And we got some great responses. Pierre, would you take us through some of these?
Sure. Thanks, James. So good morning, good afternoon, everyone. My name is Pierre Choquet. Prior to the webinar, we sent a survey to the registrants, and we asked you the following two questions. What is smart geotechnical monitoring? And what are the emerging trends in geotechnical monitoring? And we got a lot of very interesting feedback. I'm showing here the responses we got to the first question, and I'll show you the responses to the second question at the end of the webinar. As you will see here, there are two main themes that emerge about smart monitoring. The first theme that we've highlighted in yellow is automated monitoring and connectivity in real time. This came back in almost all responses. And I think that the industry is there now. Very cost-effective and field-proven devices are now available from several manufacturers to provide automated measurements of geotechnical instruments. And you don't need any more a long factory training before installing and commissioning these devices in the field. They have become much more intuitive and it's easy to use. An example is that you can now scan a QR code of a given instrument, and all its calibration factors will be automatically configured in the data logger node to which you have connected to. Automated monitoring of geotechnical instruments benefits also from all the improvements that are happening in the Internet of Things. Our industry is at the forefront of this new trend, and in many ways it can also be considered as having been one of its pioneers. And the second theme that emerged from the survey that we have highlighted in green is that, and I will quote one of the responses, to convert the sensor data into meaningful information and knowledge that provides decision-making support for the people responsible for monitoring the asset. To do this, there are many data management, visualization, alarming, and reporting software that are available on the market. And I think that they all aim towards the same objective. We will talk a little bit more at the end of the webinar about those software, and James will also cover that topic. And it will be part of our concluding remarks on emerging trends as well. So again, thank you for your responses to our survey. So today we will make the case that the digital evolution of geotechnical monitoring enables also smarter geotechnical monitoring. So what is smart geotechnical monitoring? I will suggest that it is an evolution of what we've always done, but the range of choices and options that we have nowadays requires us to be more critical on what to do and how to implement the monitoring program while not falling in the trap of collecting gigabytes of data and ultimately not using it at all, or so little as compared to what is really useful and necessary for the geotechnical project. So the first component, a mindset. This one has not changed. Monitoring is about collecting geotechnical key parameters like pore pressure, displacements, and earth pressures in order to answer specific questions that can be related to the site investigation, the stability, the short-term and long-term performance, the construction process, and the effects on adjacent structures. So the teachings of the late John Donnicliffe and Ralph Peck remain as valid now than before when they said that every instrument needs to have a purpose. The second component is a tool set. As you know, the range of monitoring instruments and techniques, either in-ground, on-ground, or above ground, has multiplied over the recent years. In-place inclinometers and shape arrays have now mostly replaced manual inclinometer surveys. Settlement profiles can now be monitored using horizontal shape arrays. Fiber optic can be used for distributed sensing of strain, temperature, and vibration. Geodetic instruments such as robotized total stations and GNSS are very common. Ground-based radars, UAV LiDARs, and UAV photogrammetry are making a lot of progress. And satellite INSAR is now an established remote sensing method. This is a lot of technologies to choose from. Not every monitoring project can afford all of them. So there is certainly a need to prioritize which one to use and again ask oneself the question, what do I want to monitor? The third component is an evolution. This illustrates that not everything will be implemented immediately at the beginning of the project. Instruments will be deployed during the site investigation, construction, and operation stages of the project. For example, during constructions, some instruments will be installed in the foundation of the future water dam or tailings dam, or in the ground behind a future retaining wall, or on buildings along the path of a future tunnel. Data loggers will already be installed at this stage, as several projects require to establish a baseline during a few weeks or months prior to the start of the construction. Then, as the project evolves, additional instruments and data loggers will be installed, and the data visualization software will be implemented, and the visualization screens will be configured and improved in order to suit the needs of the various stakeholders of the project. And finally, the fourth component is a collaboration. And there are many participants to this collaboration: owners, designers, contractors, manufacturers, and integrators. They are all, I will say, equally important in the success of the geotechnical monitoring program. The owner must recognize in advance the benefits, including the savings that will result from a properly designed and implemented geotechnical monitoring program, and must mandate the designer to plan and specify a suitable program that will provide those benefits. The contractor's role will be to recognize the importance of the performance monitoring program and how it will not only be useful for the owner, but also for themselves as a tool for risk management and cost control. The contractor must also facilitate the implementation of the monitoring program and collaborate with the designer and the integrator so that the program will be implemented in the most efficient way with minimum disturbances to the construction process. The manufacturer's role is to collaborate with all stakeholders and to make the effort of understanding the objectives of the monitoring program in order to assist in selecting the most suitable type of instruments, data loggers, and data management and visualization software. The manufacturer should also always be in listening mode in order to take every opportunity to improve their instruments and make them even more robust and easy to install and troubleshoot. And finally, the integrator has also a very important role in installing and maintaining the geotechnical and geodetic instruments, data loggers, connectivity, and remote sensing, and integrate them in the data management and visualization software, as well as being in constant contact with the contractor, the designer, and the owner, who are the final users of the data. So let's now spend a few minutes on the evolution of geotechnical monitoring. I'd like to go back, to start by going back in time with you to 1979. This is me as a young engineer sporting my aviator glasses that were very trendy at that time. I think that nowadays there's only Joe Biden who has such glasses. RST instrument had been founded 2 years before in 1977, and this year we will celebrate our 45th anniversary. Vibrating wire instruments were just starting to be manufactured in North America, and the IBM PC with the DOS operating system was to be released 2 years later in 1981 at a price in excess of $1,500 with 64 kilobytes of RAM memory and 160 kilobyte external 5-inch floppy disk drive. So you can imagine that we were only at the beginning of the digital evolution of our industry. So geotechnical monitoring has evolved a lot in its history. That means over almost a century, but of course with a considerable acceleration in the past 40 to 50 years. And this makes me realize that I may have witnessed a not so negligible portion of that history. I can remember in the late 70s when a professor was trying to explain to my colleagues and myself what was a vibrating wire. And I couldn't figure out what was that oscillating steel wire had to do with measuring a water pressure or stresses in rock. Then in 1979, I became part of the monitoring team as a graduate student of the 13-kilometer long, 8-meter wide Frisian tunnel built in the Alps that was under construction between France and Italy. And I'll tell you that I would have liked that data loggers be invented at that time, because I had a good 50 vibrating wire concrete strain gauges and piezometers to read every day, in addition to measuring conversions across the 8-meter diameter using a tape extensometer. By the way, I would have also liked if Excel had been invented at that time, because I had to plot all that data by hand for my daily and weekly reporting. So starting with piezometers at the left, they started more than 100 years ago. It is known, for example, that open piezometers were used in the late 19th century in India to study seepage flows under irrigation dams built on alluviums. And hydraulic piezometers were invented not too long after that. The one shown on the left was developed by the U.S. Bureau of Reclamation in 1940. And all over the 50s, 60s, and 70s, hydraulic piezometers, like the one shown right beside, have been used extensively in many embankment dams all over the world. And many of them are still functional and are still being read nowadays. But fast forward today, and vibrating wire instruments, and especially piezometers, have now mostly replaced pneumatic and hydraulic instruments. And one of their main advantages is that they can easily be read by data loggers. And who knows what the future holds? Maybe we'll be able one day to read distributed pore pressure every centimeter along an optical fiber grouted in a borehole. Inclinometers have also evolved considerably since Stanley Wilson invented them in 1952. And although manual inclinometer surveys using an inclinometer probe lowered all the way down a borehole are still very common, it has now become very commonplace to install a permanent string of inclination sensors in the borehole, such as the shaper illustrated here. And again, one of the main advantages of this evolution is that the string of sensors can then be read with a data logger. In terms of readouts, you can also imagine how bulky and delicate the first readouts for vibrating wire instruments were. The one illustrated here on the right-hand side is from the 50s. And nowadays, all those vibrating wire instruments can be read by small battery-powered data loggers that transmit measurements by radio, cellular, or satellite mode back to your office. As for data loggers, this is the first data loggers that I used back in 1989, together with Professor Gene Hutchinson of Queen's University as part of her PhD work to read about 3 dozen cable boat strain gauges in an underground mine in Quebec. That box weighed 25 kilos, and it was powered by 110 volts AC power. And I can't remember how much we paid for it, but I think it was around $5,000 to $6,000 in those days. And data was recorded on a 5-inch floppy disk that we had to go and retrieve on the ground in person every week or so. Needless to say that data loggers have come a long way since then. This applies also to data management and visualization software, where Excel is now replaced by various dedicated geotechnical monitoring software that are used today and that are designed to better manage and visualize the large quantity of monitoring data that we're now able to collect and help us also to manage alarms and facilitate reporting. And finally, surveying and geodetic methods have also evolved considerably with the advent of motorized total stations, 3D laser scanners, UAVs, terrestrial SAR, LiDAR, and satellite INSAR. And my colleague Parwant will now present to you the evolution of INSAR. Up to you, Parwant.
Thank you, Pierre. Let me just take control here. Okay, perfect. Hi, everybody. My name is Parwant. I have been doing INSAR since 2003. In my first 6 months of practicing INSAR, I processed a grand total of 3 images. An earthquake had occurred over the Denali Fault in Alaska, and I spent 6 months analyzing these 3 images to map the displacement caused by this earthquake and also map the extent of the damage. Now, fast forward to today, and we at 3B Geomatics process tens of thousands of images every year. So INSAR has come a long way. It has evolved a lot. In thinking about this evolution, it's useful to think about it along 4 different aspects. I mean, our goal with INSAR has always been to provide an early warning before risks are occurring on the ground and before they become a problem. But the progress we've made is, first and foremost along the coverage aspect. So in the past, even 10 years ago, INSAR mostly worked in static environments, arid environments, such as oil and gas fields, or over cities, which change over years and decades. But today we can handle construction, vegetation, and snow, which basically opens up new applications such as mining, which is really well established now, pipelines, and even areas with permafrost in the Canadian North. Second, we have detection. In the past, there were a lot of gaps when it comes to detecting displacement that is significant for the clients, but these gaps are few and far between now. We're able to detect subtle displacement, strong displacement, really local fault-like displacement, widespread displacement, new displacement, accelerations. And furthermore, we are able to highlight each displacement hotspot that matters to the user. Next, we have speed. So in the past, INSAR data are massive. We have petabytes of data in our grid computing environment and in our server rooms. In the past, it would take days or weeks to process this data, which means that the report goes to you many weeks after the event occurred and really takes away from the usefulness of the report. To know something happened, a month ago is not as useful as finding about it today, which is what we can do right now. So the processing speed has reduced from weeks to hours in the last 10 years. And finally, we have delivery. So INSAR reports used to be very cumbersome, massive geodatabases. I remember shipping out USB drives with these giant geodatabases and mailing them out. But today, all this data is delivered seamlessly through the internet, and it's in your hands very efficiently. Just a quick refresher on INSAR for those of you who may be new to the technology. So INSAR gives you 3 pieces of information: where, when, and how much the ground is moving over very large areas. So what you see in front of you is a tailings pond in Fort McKay in the oil sands. And you see areas that are colored, like the green, yellow, red colors, and then you have an optical image that's shining from the background. So wherever we have colors, there are measurements, and there are millions of measurements. And then the areas where the optical image is shining through, that's where we have a lot of surface disturbance, where liquids are pooling or some surface changes happening at a faster rate, at a faster speed than the frequency of satellite images. So wherever you do have coverage, you have the green color, which signifies no displacement, which in itself is very useful information. And then on top of that, you have the yellow and the orange and the red areas, which signify displacement away from the satellite, and the blue areas, which indicate displacement towards the satellite. Now you can click on any one of these millions of points. For example, here I have clicked on one of the orange points, and you can see the displacement profile of this point over time. So you see the movement, and then there's some gaps where probably some snow fell and measurements could not be made. So let's go back to these four aspects along which INSAR has evolved. So the first one is coverage. So here we have a mine site. And on the left, you can see that, you can see all these green and orange red areas. They cover about half of the optical image. This is because only permanent targets have been processed in this processing regime. INSAR practitioners were obsessed with processing targets which are always there for months and for years or even for decades. Now, these are very good targets, but you might note that the most interesting areas, such as the mining pit and the tailings dam, they don't even have coverage because they are areas where the targets are being reset very quickly due to digging, dumping, excavation, blasting, etc. So 3V Geomatics innovated a processing regime called temporary targets. So we co-processed not just the permanent targets, but also the temporary targets together to get basically complete coverage. As you see on the image in the right, we've gone from about 5 million measurements to 11 million measurements on the right, and all the interesting areas are covered, and you can see the extent of the displacement as well. And there's lots of new areas that were not actually visible on the left. So this has really expanded the reach of INSAR, the coverage of INSAR into the more dynamic areas, which are actually much more interesting to users. Now, vegetation is not the friend of INSAR. INSAR typically uses very short wavelength satellites. So the wavelengths may just be a few centimeters, which allows you to get down to millimeter precision. But this also means the short wavelength microwaves, they bounce from the leaves, they bounce from the canopy. They cannot penetrate the vegetation to make measurements on the ground. If you use a short wavelength sensor over a vegetated area, you get an image like the one shown on the left, where you have kind of patchy coverage. It looks fairly noisy. It's not very useful. 3VG operationalized the use of long wavelength sensors. So these sensors have a wavelength of 24 centimeters, which penetrates through the vegetation and makes measurements on the underlying ground. So you can see basically in the right image, you have the red pipeline right of way, and flanking this right of way, you can see nearly complete coverage using this long wavelength sensor. And then you can see this blue hotspot flanking the pipeline that is potentially threatening the integrity of the pipeline. Now you do sacrifice a little bit of sensitivity. You are at centimeter sensitivity, not millimeter sensitivity, but that is a very good trade-off given that you can still identify fairly subtle displacement and get nearly complete coverage over vegetation. Okay, next we have snow. So about 10 years ago, nobody bothered monitoring environments that have snow because it's just more difficult. But we've taken an approach using these temporary targets that I described earlier, that if you have images throughout the year, which are not throughout the year, but in the summertime, which are snow-free, you can just use these images. And in the early fall and the late spring, you may have some images which are partially snow-free, and you can use the areas of the image that are snow-free to basically get, like a piecewise monitoring history. So the displacement map that you see in the background, it looks more noisier. It's got more of this like salt and pepper kind of noise because there are fewer measurements during the year. Also, if you look at the time chart, you see there's gray gaps when there was snowfall or snow melt. And you also see some orange dots where measurements could not be made due to snow. But nevertheless, this is very good information. A lot of pipelines are in snowy environments. Even some mines are at high altitude and they get a lot of snow. And then of course, you have like Arctic communities, which get a lot of snow. So it's now possible to monitor pipelines, permafrost, mines, and snowy environments. Okay, once we have coverage, it's important to talk about detection. Can you detect what matters to the user? Can you detect all the significant displacement? So about 15 years ago, the resolution of the INSAR satellites was about 20 meters, which gives you a coarse measurement, a coarse resolution over a zone of displacement. So for example, look at the image on the bottom left. This is the tailings dam, as you see in the optical image. And then if you look at the image on the right panel, you kind of see this washed out displacement map. The reds and the oranges and the yellows are not very distinct from each other. The extent of the displacement are not very clear. With modern satellites, we're down to 3 meter, 1 meter, even sub-meter resolution. So in the middle panel, you see the kind of resolution you get with 3 meters. You can see all the features very clearly. You can clearly see the extent of the displacement. And this is much more useful than a coarser resolution. This becomes even more clear if you look at the points generated by INSAR. So in the figures on the right, the top figure shows 10-meter resolution, and the bottom one shows 3-meter resolution. So the number of points goes up by a factor of 10 because you have, 3 meter in X and in Y, so 10 times as many points. And now you can see very local displacement, which is circled in white, and you can click on these points to see their displacement profile over time. Next is the frequency of the satellites, and by frequency, I'm talking about the revisit of the satellite. So, about 12 years ago, satellites would come around every 35 days or every 24 days. Now it's down to twice a week, and going forward, it's daily. So if you only get 8 images a year, as shown in the image on the left, you can see the general trend line of the displacement. But this is a far cry from 16 images per year, which is shown on the right, where you not only see the general trend, but you can see 1, 2, 3 different acceleration events. And you can highlight these to the user as soon as they occur. The bottom line is if you don't acquire enough images during the year, you're not going to get as much of an early warning. The next big thing is highlighting displacement. In the past, INSAR data deliveries were these huge data dumps. Here you go, here's all the data. And then the user has to look through it and sift through it, identify all the features that matter to them, and so on. Now, many years ago, we innovated a statistical error analysis of all this displacement data. So for each of these hundreds of millions of measurements in an INSAR displacement map, we asked the question, is this displacement distinct from 0? And how distinct is it from 0? So you can say with 95% confidence or 99.9% confidence which pixels are definitely moving. So you can make these contours using this kind of analysis. So this image shows the outermost contour. We can say for sure that the pixels inside the outermost contour were 95% certain they're distinct from 0. And for the innermost contour, we're 99.9% certain. Now extrapolate this to tens of thousands of square kilometers as shown in the image here, and you really see the impact. So here we have a pipeline shown, the right of way is shown in blue, that's traveling over thousands of kilometers of vegetated terrain. And then using INSAR, we can get nearly complete coverage over this area. We can identify hundreds of hotspots of displacement, and we can provide an inventory, like a database of all these hotspots. Now you as the user can also bake in other constraints, like for each hotspot, we can tell you the severity of the hotspot, the significance of the hotspot, but also, you can take into account the distance of the hotspot from your pipeline, and also the local slope. Is it facing the pipeline, which is more dangerous than if it's facing away from the pipeline? So speed has been a game changer. I only have one slide on this, but speed means the speed of data processing. It has a software and a hardware component. So on the software side, there's a tracking database that tracks each of these thousands of images all the way from planning to acquisition to data download to data processing to online delivery. And it's a fully automated processing system to the extent that the human QC is optional. And this is underlain by a lot of hardware. So not just CPU processing, but tons of GPU processing, and also a distributed storage system that can actually process petabytes of data very quickly. So the final piece is delivery. Modern day delivery systems. So we have built a system called Motionary that some of you may have used. It's an online system. It's a web-based system. Basically, all the data is in the palm of your hand, in your cell phone or your tablet, or on your desktop. So in the top panel, you see, millions of measurements, and the ones which are significant are outlined for you in purple. And then you can zoom into any of the points as shown below and, plot their displacement profiles. So there's no need to install any software. We are continuously adding new features to this based on what our users are telling us. And as new images are acquired, the data is also just updated on the fly. So there's no need for cumbersome big deliveries. Okay, now let's look at some practical applications. Okay, this is the Yanacocha mine in Peru. A contact of mine reached out to me about the site. And, there's publicly available Sentinel data over the entire Earth, actually, that is collected, roughly twice a week or once a week in some areas. So I took 2 years of data, so about 120 images, and basically hit a button in our software to download these images, and they were all processed overnight. And I had this result in the morning. So we have nearly full coverage over 300 square kilometers. We have very good detection. We have detected about 50 areas. And also note some of the highlighted areas are green. So, very subtle displacement, maybe a few millimeters per year is occurring there, which can be picked up by INSAR. And after this, you're off to the races. So Pierre is going to talk a little bit about what a mining geotechnical engineer might do with this type of data.
Good, thank you, Parwant. Let's try to answer that question. How do mining engineers react when INSAR informs them of an area on a tailings dam where new movements are detected? So I'll start by saying that movements is not new for mining engineers. Mining engineers are exposed to movements and displacements everywhere on their mining property. The open pit walls slope, they move. Tension cracks appear at the crest of the pit. Tailings dam slopes, they move as well. Cracks and settlement is very often observed at the crest of the tailings dam. So the challenge is to apply good engineering judgment and, of course, to react promptly. So after INSAR has identified movement on the tailings dam, and especially if it's a movement that had not been identified before, there is a number of steps that can be taken. I'm not saying that all these steps will be taken, but that's certainly a good list of them. So first and foremost, a visual on-site inspection, and then review available monitoring instrumentation information that you have already near the zone, piezometers, inclinometers, surveying prisms, etc. Review the local geology, don't forget the foundation material. Review the borehole logs, review the construction details and whatever information you have subsequently. And then an important one, do additional numerical modeling to back analyze the reason for the movements and refine the material properties in the numerical model. That may help you considerably. Then consider adding new in-ground and on-ground instrumentation. consider additional borehole sampling, CPT testing, possibly geophysical surveys, and eventually design remedial measures like reducing the slope, build an abutment, or discharge tailings in another area of the tailings facility until movements have stabilized. Back to you, Parwan, for the next case study.
Thanks, Pierre. So next we have this very unique and interesting case study. A client reached out to us many years ago about processing data over San Francisco. And as I mentioned before, INSAR has this time machine. Data are being collected just like clockwork without anybody tasking the data. It's just being collected like clockwork over all the major cities of the world and basically all the land area of the earth. So we looked in the archives and we found high resolution images going back to 2009. And we processed all this data, and you can see the results here. You have, thousands of points, or hundreds of thousands, millions of points actually. But these points are nicely overlaid on all these towers in 3D. And there's tons of points on each building. And the Millennium Tower, which is the building in the center, sticks out really like a red flag here. So right away, we knew something very unique is going on with this tower. And we had about 1,200 measurements on this building. And we decided to do some analysis on it that was fairly unique and unprecedented for INSAR. We basically took these 1,200 points. So, this is a Millennium Tower. We took these 1,200 points and we modeled the settlement of the Millennium Tower and also its tilt along two directions. And the results of this analysis are shown here. So in the top left figure, you can see the settlement of the Millennium Tower over time. So it sunk about 20 centimeters over 9 years or so. And then you also see the tilt on the bottom left. So it tilted about 50 or 45 centimeters over these 9 years. So from the base of the building to the top, it tilted towards the southwest, as it turns out, by 45 centimeters. And on the right, you can see these are the rates of the settlement and the tilt. So these rates are not constant. There were some accelerations and decelerations, both for the settlement as well as the tilt. So INSAR data, along with the other ground instrumentation data that was available or that was specifically collected, it's being used. You can search for Millennium Tower on the internet and watch YouTube videos. This tower is sinking and tilting, and they're drilling piles into the bedrock to stabilize it and keep it vertical, basically. It's very interesting. Next, we have a case study over Peace River. There's a dam on this river. James is going to talk more about this, but we did an INSAR analysis. We used this long wavelength data over this very vegetated area. You can see dozens of red hotspots and potential risks in this area. And the red rectangle shows where RSD has some instruments deployed here as well. Over to James.
Yeah, thanks, Parwan. So yeah, just below that rectangle, you can actually see Site C Dam, which is a large dam in northern BC, Canada. And back in 2018, RSC was actually involved installing and setting up a automated data acquisition system. So on a site like this, you might have a number of multi-point borehole extensometers, inclinometers, shape arrays, piezometers, and it's a lot of work to read them all manually. So something like this is where setting up an automated system can really pay off. So this is from 2018, but a lot of this still rings true today. A lot of these networks kind of look like this, where you have all these nodes, data loggers around your site, and they all connect back to central hubs via some kind of radio transmission. There's a number out there, and they've changed, obviously, over the number of years. But you have everything from like Sigfox and LoRaWAN. I've seen some questions about that. Narrowband IoT is another way to do it. But they all go back to some kind of gateway and hub, and those have some kind of northbound connection, a lot of people call it, but that's just either a satellite connection or a cell or local area connection, so it could be Wi-Fi, back to wherever you're centrally storing your data. And that could be in the cloud or on a local server. So each of these hubs, of course, the nodes are much smaller, and they still are today. But these hubs are generally a little bit bigger just because you have a bit more brains involved at that point where you have that connection back to your server. So this would be an example of one. Small solar panel up top, bigger antenna at the very top. Farther down, you have that kind of box with the brains in it. And so all those nodes would be kind of pointing to one of those stations for that area of the site. And you'd have a number of these around your site. So this one is conveniently by a site office. So wherever you can have site power, you should take advantage of it. Just solar power is just one more thing to deal with. So for something like this, you just use site power to power that station. But of course, it's not possible for every application. Sometimes you have, even for your site, what would be considered a remote location. So again, you have solar panels there, and all those nodes in that area can communicate back to that gateway or that hub. So all this data is great, but you really need some way to interpret it and digest it. And there's many ways to do it, but you ultimately want some kind of visual representation. And this would be an example of a shape array. So the green or purple would be your deformation. So we're looking at cumulative displacement for this instrument. And oftentimes on any instrument, you also want some kind of error bars, or sorry, alarm values. So you have yellow ones, which could be your low value alarm, and your red one, which would be your high value or more intense alarm, however you want to define that. And you see that change with time. Similarly, you could look at the incremental displacement. So if you really want to get on a granular level change for the instrument, for those parameters as well, you can do that. And again, alarm those values too, because sometimes your alarm or your notice to make a change on site might be a combination of cumulative and incremental. Similarly, you want some way to visualize and interpret your extensometer data and your piezometer data. Plotting them up together over the same time series or even on the same plot can be a really useful tool to interpret what's going on at your site. There are multiple ways to visualize it, and there's multiple pieces of software out there to do it, but they all kind of follow a lot of the same key features. And you should look for this, I guess, when you're evaluating what you're going to use to look at your data. So you should have a dashboard of some kind to give that 1,000-foot view or 10,000-foot view even of your site. And that should give you, well, a snapshot of what's going on. And so look for a real-time display, so maybe even alarms at this level, so like green being okay, yellow a threshold, red alarm. You can gain some insights at this point. And then start to navigate around your site. So maybe click on locations, see instrument data. Again, see the relevant alarms, see the history of the data. That can give you a lot more information versus just a single value. Another great tool is a file converter, or some way to take the data off the site, to use maybe a legacy tool that you have, or maybe you have some great spreadsheet that you still really like. That's fine. It's great to be able to pull that data off and interpret it the way you're used to, as well as access controls. So if you have thousands of instruments on a site, probably not every single person is interested in every single instrument. Or maybe there's different consultants working on different portions of the site. And so it's important to be able to give the appropriate permissions and controls to the right groups, as well as virtual variables. So that's what we're calling, if say you have multiple instruments that you use the information together to gain an insight, some kind of calculation, and that calculation can happen in real time, so you're not doing it every single time you're analyzing the data. There's a bunch of other useful features that you should be looking for on these dashboards that I'll highlight, some of the ones I like the most. Data validation is often overlooked, so having some kind of QA/QC on the data that comes in. Sensors can give off readings for any multitude of reasons. So I think a lot of people have experiences with noisy data. So being able to set up some kind of filtering that you have an understanding of is nice, so you're not setting off a bunch of alarms unnecessarily. An open API access is great. There's lots of tools available to analyze data today, and there will be more as technology progresses too. So just being a little bit forward thinking in that regard can really pay off. And reports. A lot of us are still really used to PDF reports or even handwritten reports. So anything you can do to assist in that workflow, there's a lot of ways to automate those now. So you just print off those visualizations or even the records of alarms, and really takes away a lot of the busy work of providing reports every week or every other day. Another question we asked before the webinar were, what are the emerging trends in geotechnical monitoring that a lot of you are seeing? So I'll invite Pierre back again to walk us through some of these.
Good. So, yeah, we'll now conclude the webinar by reviewing the responses that we received for the second question. What are the emerging trends in geotechnical monitoring? So similarly to the first question, we've been able to group responses in two categories. We've highlighted in yellow the responses that pertain to the objective, and I'm quoting again, allowing the user to quickly understand the issues happening at their assets. In this category, we're seeing the hope of even simpler implementation of automated monitoring and a suggestion of correlating monitoring and numerical models. So that goes in the same direction as the trend of digital twins. Another suggestion is to use computer libraries like OpenCV for computer vision, and this goes then in the direction of artificial intelligence. So there will certainly be more and more applications of artificial intelligence in our geotechnical monitoring, considering the vast amount of data that we are now generating. And in the responses highlighted in green, we see that the anticipated emerging trends are in satellite technologies and remote sensing, so INSAR and drones. I would also like to add to this my personal view that I agree with the emphasis on simpler automated real-time monitoring and better data visualization and interpretation. But I think we should also not keep the status quo on the sensors front. I see improvements on sensors as well. Some have already happened in the recent years, and some that we still need. For example, we're now better at monitoring very small ambient vibrations on earth, steel, and concrete structures, monitoring distributed horizontal and vertical deformation in the ground, distributed temperature profiles for seepage detection, multi-point pore pressure in soils and rock. But we can still improve our sensors. For example, we still need to understand better the phenomenon of a static liquefaction, especially in tailings dams, and to develop better sensors suitable for it. I suppose that such a sensor would be an in-ground sensor, but who knows? So on-ground sensors and remote sensing will certainly see many new developments as well. So I will ask James to do a few concluding remarks.
Sure, thank you. Yeah, so thanks everyone for attending. Again, we're from Terra Insights. So that group of brands of RST, Measurand, 3B Geomatics, and Syscom. And within this now group, we have a number of solutions from geotechnical monitoring, geospatial monitoring, data collection, visualization, and connectivity. So we do have some time for Q&A. Looks like 10 minutes. There are a bunch of really good questions. I'll go through, we're not going to get through all of them. We'll try to get through as many as we can. First question here was, is this a LoRaWAN system? The system presented today actually was not, or isn't today, but Affinity, the product from Terra Insights, is a LoRaWAN system, so it is available. The next question is, when the stated specification mentions continuous data collection, what is a good time frame set for gathering data? Some say continuous is every second, which gives us a lot of data. Some specs require every 15 minutes or every hour. Is there consensus on the term continuous? So I'd also welcome Pierre or Parwan on their impression of this too, because I think this comes up a lot. Just in my personal experience, I very rarely see specifications calling for more frequent than hourly. I think it comes down to how often is a human at the end of the day actually going to look at and analyze the data. If you're getting data every second, there's an argument that, well, maybe you should be watching it full time. It seems like a pretty risky project. But it'll depend on the project, and oftentimes an owner is going to specify their own monitoring interval. Parwant, Pierre, anything to add to that?
Yeah,
Well,
I mean, go ahead, Pierre.
I was going to say very briefly. There is the option, of course, of monitoring a certain the main critical sensors at a reading interval that could be almost close to a second. Actually, that's feasible if it's really one that is related to a failure mode on which you would like to have alarms. A good consideration is not all sensors need to be monitored with the same interval.
Yeah, I'd agree. That's great. Okay, so I think this is going to be one for Parwant. This question, hi, what is the actual precision of INSAR movement detection nowadays?
So the precision, it's definitely sub-centimeter. There's a few factors that come into play. So, these long-term targets that I talked about, I call these permanent targets. So they're around for years and decades. They're not disturbed. You can get down to millimeter precision on these targets. For targets which are disrupted frequently, so think about a mine site where there's a lot of blasting happening, or digging, dumping, etc. Then these targets are being reset every few weeks, every few months. So you only get a few satellite images on a given target before the target gets reset by these human activities. So you will get lower precision for these depending on how long the target lasts. It's a competition between how frequently are you getting satellite images. Like you're getting satellite images, let's say once a week, right? And how fast is the ground being disturbed by people? So the longer, the more measurements you get over a given target, the greater your precision. So it can be millimeter for permanent targets, maybe 5 millimeters or 10 millimeters for a temporary target, depending on how many measurements you got. And then finally, the other aspect is just wavelength, right? If you're using a short wavelength, so 15 millimeter wavelength or 30 millimeter wavelength, then you're going to get down to your millimeter precision or 5 millimeter precision. But if you're monitoring like densely vegetated areas, you can't use these short wavelengths. You have to use the long wavelengths to penetrate the vegetation and make measurements from the ground. So now you're using a much longer wavelength, like 24 centimeters, and you're measuring fractions of that. So you will get centimeter precision rather than millimeter precision. But what we find is that, while we're here chasing millimeters and so on, these kinds of precisions are very good. They're more than necessary, more than appropriate for, all the different applications that I talked about in my presentation.
Great, thanks. This is another one for you. I apologize, but I know I get this question a lot too. Is it possible to use INSAR over the snow cover?
I mean, over snow cover, there's a few things here. So, let's say the snow has already fallen and the ground is frozen solid, right? Then yes, INSAR works. Like you can measure, make measurements, but basically you're measuring the frozen ground, like you're measuring properties of the snow and stuff like that over frozen ground, which is not what users want. If the ground is frozen solid, then it's not, really moving very much. It's not interesting. So for that reason, a lot of people will pause monitoring over the winter when the ground is frozen solid, for example, in Arctic environments. Now, having said that, like it's interesting to monitor an area which gets snow periodically for the reasons that I mentioned. Like a lot of pipelines are in snowy environments, and a lot of mines are at high altitudes. So basically, think of it like if the ground is snow-free, that's when you have those repeatable targets, right? That are consistent from one image to the next. Because snow is not consistent over time, right? It's always changing, right? So when the ground is snow-free or parts of the ground are snow-free, you have those consistent repeatable targets, then we will use all the parts of the image which are snow-free, and in the summertime, we'll use entire images that are snow-free. So you get this like interrupted monitoring or piecewise monitoring over time, which still has a lot of value. Now, some clients do go for, this is rare, but some clients do go for like uninterrupted monitoring throughout the winter. So they'll ask us to install like corner reflectors with snow covers, or there may already be such reflectors at their site. And so these kind of special targets, which are kind of snow-proof, they can be tracked throughout the year, regardless of snow. But please bear in mind that the costs for these reflectors are not insignificant, and they also require maintenance throughout the year.
Right. Thanks. I think that was actually one of our other questions that I saw about corner reflectors. So appreciate you getting that. Pierre, I think this will be a great one for you to answer. The question is, how does the MEMS inclinometer's drift over time impact your measurements, and are you able to account for this in software?
Good question. So I'll say for MEMS inclinometer drift, the devil is in the details. And we've looked at it very carefully. So we have a new generation of IPI that has been introduced 2 years ago. You can consider that if there is a drift in the IPI, a good portion of it comes from a mechanical adjustment of the components. I mean the joints between the sensors and the extension base and the next sensor and so on. So yes, I think that all manufacturers will recognize that when you install an IPI, you have a settling time of maybe 1 day, 2 days, something like that, during which all these adjustments take place. So don't take your baseline the first day. Look at your data and determine the time at which you will make your baseline. This being said, in our case, we now realize that with the new generation that it's very quick. It's 1 or 2 days. ISO 18654, the new spec, the standard on geotechnical monitoring that covers piezometers, inclinometers, and so on. They specify a 24-hour stability for the sensor itself. So not the whole string of IPIs or shape arrays, for the sensor itself. And I think it's a value something like 0.01 degree over 24 hours. So that's to qualify the sensor itself. But they have a spec also of a stability of the horizontal movement the detection, if you will, of an IPI over a length of 30 meters. I think they spec plus or minus 2 millimeters over a string of 30 meters. Our spec is 0.05 millimeter, 0.5 millimeter over 30 meters. So we're much better than the ISO spec. So I don't think you should account and that you will need to account it in the software, although it would become a bias if really you wanted to account for something. It's more the installation, the way you do it, the care that you take for doing the installation, and then considering that initial 1 or 2 days settling time.
Awesome, thank you. I think we'll try to hit 2 more last questions here. One is, if we want to share information between one of your systems or data loggers to the plant control system in a plant, which protocol do you use to send this information? What's commonly set up is you set up an API poll from our database to whatever you're using. You could also set something up in the form of an FTP sharing site. So if you want to share the exact CSVs, that's another way to do it, just less elegant. We'd recommend putting in a little tiny bit of work to set up a functional API. And one last question is, what are systems capabilities with respect to incorporating AI and the future prospects for doing so? For example, can the system yet recognize whether deformations may be related to settlement, heaving, erosion, landsliding, etc.? Parwan, I think probably have you talk a little bit about already the level of AI in processing INSAR data. I think there's a fair amount involved at that level, and where you see it maybe going beyond where it is right now.
Yeah, I mean, we use a little bit of AI in our processing pipeline. So, so machine learning specifically. So the processing pipeline is not a single step. You have the radar image coming in, and then you may have 20 steps, so 20 different modules or algorithms that process the data. So like you align the images together, you filter them, and modeling, and so on and so forth, right? So some of these steps do use machine learning, and they now produce better results than traditional algorithms. But I think this question is more directed towards like the end product. Like, are we classifying different types of displacement using AI? This is something we have thought about, but we're not doing this currently. So, like in the case of the settlement or heave or it's fairly obvious. Like you will see it in the rate. Is it red? Is it blue? If it's red, it's settlement. If it's blue, it's heave. But I think, if I'm not mistaken, this question might be more directed towards like what is relevant for a user. So for example, for pipelines, right, you can have soil dynamics, which are cyclical. The ground goes up and down and up and down. That may be less interesting for a pipeline operator than like a landslide, settlement, these more one-time events or linear events or nonlinear events, So distinguishing between the two and like telling the user this is important for you and this is not important for you, that currently seems like a little bit of a stretch for us to make that judgment. I mean, we do have advanced systems where someone gave us labeled data for like one, let's say you give us labeled data over 100 square kilometers and tell us, these are the soil dynamics, we don't care about them, and these are the types of events we care about. We can basically train a machine to extrapolate that to thousands or tens of thousands of square kilometers. But on our own, independently, we would refrain from making those kind of decisions, what is relevant or interesting to a client versus what is not so interesting.
Yeah, I guess every AI application all starts with good training materials and evaluating it before you're making recommendations. So I think that's probably more where the stage that is in right now, would be my guess. Yeah, okay. Well, I think that's a wrap on time. Apologize we didn't get through all the questions. There will be those materials coming out afterwards. There'll be a recording as well. Thank you very much. I have a feeling we'll be doing a few more of these, so I'll probably see you soon.
Thanks, everybody.